Hello, Rayazul. All of you get the mail regarding this session now.
Yes, sir. We have got mail.
Okay. Actually, in the previous session, there are the 10 to 15 people. But
Yes,
today
sir,
they
today I am only there. Hello. Hello.
hello.
Sir, I have a question. Like, do we
Please.
need to be an expert in Python for
Sorry.
using this?
Please. Can you please repeat?
I am saying, do we need to be an expert in Python?
I think it is not. It should be ideally, but if you are not expert in the Python, it also can work. Like just limited knowledge about the Python,
Okay.
like how to load your data, how you can use that data in terms of like standard scalar terms and if you get expertise in some libraries like pandas and sklearn, you can do your work.
Sir, any suggestions how we can learn those things? Which platform we should use?
For any suggestion, you can learn some basic Python that will help you. Like basic Python, like few libraries, as I told, some how to use the pandas and sklearn.
Like, I am asking if I should take some courses from Coursera or Udemy. Like,
You can take those in terms of learning the Python.
okay, okay, sir. Thank you.
Both of you have your PC or laptop?
Sure.
Yes. Sir.
Okay. Okay.
Yeah, last time we used some libraries.
Last time we used like pandas and NumPy and sklearn especially.
Yeah, that I don't get how sklearn works. It's like
Yeah, because sklearn has by default some models, some ML models which we have used last time, like linear regression. Last time we just used linear regression, and today I will try the other models also.
okay, sure. Can you share some materials regarding that? The libraries we
Okay,
used in our course.
last time which we used, I shared all of the things like data and the code.
We got that data and code, but some basic stuff like which library, what is function, what it contains. It's like we are new to those library, right?
Okay, okay. So I will try about that, but I can't make a promise to share those things because I have to look for from where I can share those things.
Okay. Yeah,
Okay.
no problem.
but I will try. Before the next session, I will try to share to all of the things.
Yeah, thank you.
Uh, Reazul, you can use Coursera. Otherwise, you can also go for the YouTube. There are lots of video about the Python and for the material science also. Okay, let's share screen. Are you able to see my screen?
Yes.
Okay. Oh. Hello everyone. I'm Shivam Aggarwal, PMRFTA for this course, Artificial Intelligence and Machine Learning in Material Engineering, which is being instructed by Professor Krishanu Biswas from IIT Kanpur. And welcome to all of you in the fourth live interactive session. from the last time we have started about the how machine learning can we use machine learning in terms of predicting anything and how we can utilize this tool especially in the material science. So in the last time we see about that and how, and we also discuss about the workflow. In the workflow of the material science, we have divide the workflow in the 5 parts. We can divide in the 5 parts, but it is not limited to that. You can divide into the 4 parts and in just 3 parts also. And you can also add some other parts like model analysis, etc. So in any machine learning work, first of all, you have to prepare a data set. That is called the data preparation. And in the machine learning, machine will learn from that data. So we have to very precautious about the data what we are going to use. And then there is a feature engineering, like the data set should be should be converted into the some features that will describe your data to the machine in more precise way, like uh, like the conditions about that, it can correlate between the input and output. And after that, we have to go for the model selection. The model selection is the very crucial part in any ML work. Like model selection is what ML model you are going to use, what ML algorithm mainly. Like there are the different kinds of algorithm, some are the ensemble based, some are the neural network based. So uh, what kind of algorithm you want to use, and your what will be the best for your data. And the fourth part is about the like model evaluation. You are using the different kind of models, then you want to which model is performs well among those. So you have to evaluate those model to know which model is will be the best for your work. And after that, you are, of course, you are working this ML work for the prediction. So you can predict the properties by using these ML. So then in the last part, you can get the prediction. And there will be the another part that will be uh, can you mute? Okay. In the last part, there will be the like some analysis part. Like sometimes we don't want just prediction. We also want how we are getting that output, like how model is working. So for that purpose, we have to analysis uh, to our model how it get learns from the data. So last time we have used we start from this work which is published by the Professor Kishanu Viswas, and in this work we have done some things like maybe many of you are not there in the last session, I think. So I'm just briefing. You can get about this work from the last session also. So in that work, they are predicting the stacking fault energy for the medium entropy alloys by using the MLPNN model. So this is about the like what are the medium entropy alloy? Medium entropy alloys are the subset of the complex concentrated alloys for which the configuration entropy is between in the 1R to 1.5 R. And in the medium entropy alloy, there are the ternary and the quaternary alloys are mixed in the nearly about the equiatomic composition, like all the constituents are in the equiatomic composition. And these alloys, why people are working on these medium entropy alloy, because they exhibit enhanced strength, ductility, and they have a high fracture toughness. But why we are working, why the people are interested in the stacking fault energy for this medium entropy alloy, because it plays the crucial role in to knowing what deformation mechanism in is will be work for this medium entropy alloy. For that purpose, people are
May I ask
very
a question?
curious. Sorry.
May I ask a question? What is this R to 1.5R? What is that R stands for?
This what this is the R is the gas constant, ideal gas constant.
Thank you.
Hmm?
Thank you.
Okay. And uh, so stacking fault energy plays a crucial role to determine the what deformation mechanism will be dominating in the medium entropy alloy. And in the stacking fault energy, like if it has a lower stacking fault energy, it will lead to the slip dominating plasticity and to twinning dominating plasticity. And it will also influence the strain hardening and the dislocation, storage, etc. So that's why people are very curious about the stacking fault energy, the value of the stacking fault energy for the medium entropy alloy. How can we determine this stacking fault energy? If we talk about the experimental technique, there are the in the experimental technique there are like TAM and XRD which can be used to determine the stacking fault energy. But if I want to like if I want to choose I want to choose a material that has the particular stacking fault energy. So if I do that for the experimentally, first of all, I have to synthesize that material. Then I have to check the transmission electron microscopy of or the XRD of that material. Then I can get the stacking fault energy for that. But if I want to do for a like a group of the material, the large group of the material, and I want a particular value. So that will be like some is it become the quietly inefficient in that purpose. So for that purpose, we can just screen that thing in terms of by using the machine learning, by using the previous data. So why machine learning will we use? Because it provides a robust and the rapid method to predicting the metals property, and it is overcome the time and the resource constraint, which will be very crucial in terms of like experimental and the computational techniques, and it also enables to high throughput design of the medium entropy alloy with the defined like with the desired mainly like what is the fault energy I want, so I can screen those values from the my prediction, and I will try to synthesize that material. And it will also facilitate the exploration of the composition property paradigm, like which property is highly correlated to the our output property. So it will help us to design a new material in that way. So in this work they have uh, or in this work they have like some data which have 800 data points which have the ternary, quaternary, and the quinary medium entropy alloys, and for those composition stacking fault energy is uh, can be divided into the three parts like low stacking fault energy, medium stacking fault energy, and the high stacking fault energy. And mainly in this data set, like only 9 elements are included, like iron, manganese, nickel, cobalt, chromium, vanadium, molybdenum, silicon, and aluminium. And you can see this. And if I we can distribute this data, we can see there is the 433 points for the medium high stacking fault energy, and 236 data point for the medium stacking fault energy, and there are 149 points for the low stacking fault energy. Then there is a feature selection. What features they have used, like these data points will have the chemical composition and their stacking fault energy. But your machine don't know about the how you, the stacking fault energy will be the correlated with the composition. So you have to try to featureize your composition in terms of the some numerical value which can be understood by the machine. So for that purpose, there is a part which is called the feature selection or feature engineering. So first of all, I have to select some feature which can define your composition to the machine in the correlation with the your output property. So for that purpose, they have used some properties like elemental content ratio, Pauling electronegativity, element electron affinity, their CGLSC, and their temperature, at which temperature the stacking fault energy and ionization energy, what the number of total electron in that total number of electrons, and there are these properties which they have used to featureize their composition. But uh, their composition have the quaternary or ternary. So for that purpose, they have used P average. It means the property average. Like they have used the average of that property and the variance of that property for that particular composition. And your data will look like. Are you able to see this Excel sheet? Okay. Ah, Now here you can see the elemental ratio of the iron, manganese, nickel, cobalt, chromium in that composition, and this is the stacking fault energy for this temperature for that material, and this is the properties for that composition. So this is the Ln electronegativity average. This is the Ln electronegativity variance. So for every property, they have the two things like average of that property for this composition and the variance of that property in the composition. So they have used two things. After that, the feature selection, they have used some like hybrid feature selection method. So now, please open your browser which you are going to use, like Chrome or Mozilla, etc. So first of all, please search Colab. Maybe all of you get this completed website. Otherwise, you just search Colab, Google, and then you will find this welcome to Colab. So please click on this. And after that, please click on this new notebook. Or who joined the last session, they can open the last notebook in which they have write the code in the last session. So for the new student, please open the new notebook. All of you are able to open this?
Yes.
Okay. If anyone have facing any problem, please ask me.
Actually, I have a doubt. Like
Ah.
in last class, you told like from data we remove outliers from the data sets and stuff.
Okay.
But like basically the outlier points are the points where the lattice lattice or crystallography have exception or something like that. So is that case somewhat more important to us than the other cases?
I'm not telling that about like in the material science terms. Like I am told you to remove the outliers in terms of the like data. Like what your data you have, like from the material science or from anything else. Like you have just some random data. But if there is some outliers in the data, like just for example, your mostly of the data is maybe many of you know about the quartile, I think. Maybe I have to show you something. Maybe.
The interquartile range and all?
Yeah.
Okay.
Maybe one thing, 1 minute. Look this see this image. Like if your distribution of the data, like for any property or for your output, lie in this way, like in the first quartile, and this is the third quartile, and this is your sorry, like there is a and this is the mean of your data, and your data points is far away from this range, this distribution, that is called the generally called the outliers. And we just remove these outliers in terms of the many different ways. Some remove these outliers by manually, and you can use some there are the different technique like IQR, which also used to remove the outliers. So that will remove the outliers like 1.5 times of the delta Q from this range and from this range. So I'm not told about your outliers in terms of the like any crystallography or something else.
Okay.
Please open this link which I shared in the chat box. Okay. I have already shown you the data. What the data we have, like elemental ratio, the composition, and the properties, their average and variance. So now we are going to our code part. For any machine learning work, first of all, we have to import some libraries. Maybe there are some problem in this one. So first of all, we have to import the libraries. For that purpose, uh, you have to write we have some libraries like pandas, NumPy, Keras, Matplotlib, and pandas is generally used to handle the data frames, and NumPy is generally used to some mathematical operations for the arrays, and Keras is used for the some machine learning models. Same as sklearn is also used for that, and Matplotlib is used for the some plotting part, when you have to plot some graphs and plots. So for that purpose, you have to use the Matplotlib library. So first of all, you have to import these libraries. So for that purpose, you have to paste this code in your cell and then run by using the shift enter, or otherwise you can click on this play button type. So I have paste the code in the code share. Please copy the code from here and paste in your notebook.
Sir, I don't think I'm being able to see these codes.
You are not able to see this code. I think I have shared the share code. 1 minute. Sorry, my mistake. Sorry, sorry. I have to share this link. Right. Please open this link.
Got it, sir.
Okay. Please copy this and paste in your notebook and then run. After the importing the libraries, first of all, you have to load your data. So for that purpose, you have to actually I have the data in my Google Drive. So I have the link of that data, and then I load that data by using the pandas PD, because I have import the pandas as pd.read underscore CSV, which is used for the to read the CSV files. And df dot head is to showing the data, like what I have saved my data frame in the name by the name of df. So df dot head and bracket to is used to see the data. First of all, you just load your data. Please copy the code. After loading the data, I want to see like how like how my data is look like. So for that purpose, you have to use the df dot head and bracket. So here you can see like there is a 53 columns, and now you are seeing just 5 rows. If you want to see the more rows, so you have to write the number of rows, uh, how much rows you want to see. Like just I want to see 10 rows. Then I have to write 10 in the bracket. So I'm able to see 10 rows.
Sir, can we also have this, like, where can we access this data set if the runtime gets disconnected?
Sorry.
Like, if the runtime gets disconnected, will we lose this data set?
No, I think that will not be possible if you are just connecting the net after the some time. You can also load the data in your space also, if is the case, because you are working now on the browser, so you are also working on the internet. You are not working in your local computer.
Okay, sir.
So for that purpose, you can use Jupyter, and you can download the data in your PC, and then you can work. That will be totally like your local device.
Okay, sir.
So if you want to see what is the column in your data, so for that purpose, you have to command like df dot columns. If you want to see the shape of your data, so for that purpose, there is a code like df dot shape. I will show you. Like is the code. So the shape of our data is the 774 and 53. Like it means the 774 rows and 53 columns. Now, if you see the columns of the data, there are like these elemental ratios, then stacking fault energy, then temperature, then ECR to elemental component ratio for 2, elemental component ratio 4, 6, 8, 10, and the average and the variance of the properties. So, if I'm using the elemental component ratio in terms of elemental ratio 2, 4, 6, 8, 10, 12, so there is a no need to use the elemental ratio of the in the composition as the input. So for that purpose, we are removing those columns from our original data, and after that, I'm going to split my data into the two parts, X and Y. What is the X? X will be the like what are the input properties like and Y is the output property. Like in this work, there is a we want to predict the stacking fault energy. So for that purpose, stacking fault energy will be our output. It means Y. So first of all, I have to remove this column from the original data. Df1. So first of all, I write like which column I have to remove, and then df1, it means a new data frame will be the df dot drop. Then it will drop this column from the origin or the data set df. If you want to cross check like these columns have dropped or not, so for that purpose you have to like df1 dot columns or head. You can see here like aluminum, Fe, Mn, Ni columns are removed. And here you can also see this. So now you have to split your data into the two part. First of all, like your what is your x and what is your y. Okay. Now this is the code like what will be your x and what will be your y. So I have just write x is equal to df. What columns I have to choose for my x and what columns I have to choose for y. Now, if you want to see what is your x, then you can write a code like x dot head, and you if you want to know about the columns, then you can write about like this x dot columns.
Type is for the same as the last class by using W. We are able to access the Google Sheet. We can download from here. Mm.
So if you want to see about the Y, so you can write just Y because it is not a data frame because there are no number of columns in the Y. There is a one column, so you have to just write Y and press the shift enter. You will get about the Y. If you want to check the shape, just you can write like X dot shape and Y dot shape. Maybe all of you have done till the splitting the data set, I think. So for the feature selection, they have used some hybrid technique. First of all, they have used a wrapper for forward selection. For that purpose, they have just select only the 10 features which are highly related to the our output property. And that thing after that thing they just selected 10 features. But after that, they also used some gradient boost technique and they reduced the number of features from 10 to 7. But why we are using we are reducing the size of the input features? Because our model are get trained by using these features. So to get our data is uh, trained accurately and with the generalization. So we have to reduce the dimension of our input set because we have a very limited input just 800 points so which is not a quite large data set. If I talk about in the terms of the material, sorry, in terms of machine learning, but if I talk about in the material science, that data is very is sufficient. So for that purpose, we have to, if I want to use that data, that size of data in machine learning, so I have to reduce the size of the inputs. So for that purpose, we are using this technique, feature selection, and I have to reduce the dimension of our input set. So they use this hybrid technique. First of all, they have used the wrapper forward selection. They reduce the dimension up to the 10, but after that they use the gradient boost technique to reduce further, and they reduce 10 to 7 by using this featureization technique. I'm not going to use these techniques, and after the using the gradient boost average technique, they left with these features only. Like this feature is highly correlated to the output property. So I'm writing the code into the code here. So here you can see X is equal to X, temperature, ECR4, WASP, LSC variance, LSC average, electronegativity average, ionization energy average, specific heat average, total electron variance, and C variance, and heat of fusion average. So now this property will be act as a input property. So now my access is limited to these 7 features. Uh, Now, if you see the data here, your data is like have a particular range. Like if you see the ECR4, that is 50, 47, 31, 29. It has a wide range, like 29 to 50. If which data I can see, but there is a more points here. And if I see about the temperature, it is from 1000 to 300. If I see about the like LSC variance, it is like 1922, like 45, and it is not 45 to 4000. So it is varying from the 45 to like 4000. So every input property have a various range. So if I want to train my model, so model can be like have a problem about it because our input have a various ranges. So for that purpose, we have to reduce, we have to like normalize our input set. So there are the various methods to normalization. So here we are using the min-max scalar. What a min-max scalar will do to our data set. So it reduce like it normalize the data is the in such a way it will uh, give the zero value to our minimum value of the data and maximum value to the one. Like it give the zero to the minimum value and it will give one to the maximum value and the normalize according to that. The data point which lie between those minimum and maximum value. So it is working according
Sir,
to this
sir,
formula.
I have doubt.
Huh?
Sir, I have doubt.
Please.
Uh, how did they land up at 7
Sorry.
columns? How did they land up at 7 numbers only?
How?
How did they land up at seven data columns only?
Here we have to land about like why we select these seven only.
Yeah, yeah. How did they land up over there?
Because I'm skipping one part here, like how they got these only seven features. They got
Yes.
these seven features by using these three methods. These two methods mainly. The third one I will show. The first wrapper forward selection and second gradient boosting technique. First they use this technique to reduce the size and they reduce from 40, I think 40 plus input to the 10 inputs. And after that, they use the gradient boost technique and they find out like this they can reduce 10 to 7 features. That's why I end up with like 7 features.
Sir,
For
all
more
the
reference, you can look for the work, I think.
okay, sir. Are all these both these steps were done in this same code, sir?
Sorry.
Were both these steps like a wrapper forward selection and gradient boost technique?
We will use the gradient boost technique in future lectures. Sure.
Yeah, both are done in the same Google Colab research only, or they had used some other tool to.
Like you want the code of the wrapper forward selection and gradient boosting technique.
Yeah, like did they use this same code in the same Google Colab research only?
You can use the Google Colab for this but
Are they
I'm not
direct
using this technique
calling?
here.
No. Are they direct calling functions, or should we have to code for this wrapper
You have to like
forward?
they have in the some libraries also. So you have to like load the library and you can do these things.
Okay, it's just calling of some library.
Okay, I will try to like in the future lecture to use these techniques, I think.
Thank you, sir.
Okay, because now you are not much aware about these things. So
Okay,
many people
thank you,
are
sir.
using the first time. That's why I'm
Okay,
not at those
okay, sir.
things.
Okay, sir. Thank you.
So I have end up with the like 7 features. After that, we normalize our data by using this min-max scalar. Please copy and paste in your notebook. And now you save your the normalization data like x underscore normalized. So now you are not going to use x as the input. Now you are going to use x normalize as input of your model. Maybe you have done uh, uh, is there any problem till now?
No, sir.
Okay. Okay. Then we are going to the like a heat map. Heat map is give us about the correlation between input and input features. Or you can do this with your output property also. You can modify the like the text format and the colors of this. So you can use this library and you can find the many more things which you can do. In this website. Okay. So if you want to do more things in your image, like you want to choose some attractive color, line thickness, etc. All of things you can do from here. There are some examples. How can you tune those things? Okay. Maybe I'm sharing. Okay. Now, as I have a data, all data, so I have to like split my data into the two part, train and test. Train is for the training the model and test for the testing to evaluate the model. So, so this is the formula which are used to normalize the data and this is the Pearson correlation coefficient from which we got the correlation map, like correlation heat map. So after that, this is the heat map which they have reported in the paper, and this is the selection how they select the 7 features among the 10 by using the gradient boost technique. And they found out like specific heat average has a larger effect on the stacking fault energy. And then ionization energy average, then LSC variance, and after that the temperature, and then C variance, and then ECR. So So for the model training and the evaluation, they split the data into the two part, train and test for ratio 1. Train set was used for the training the model and test is used for the evaluation of the trained model. And they have trained the 7 ML model, 7 ML algorithm like linear regression, lasso, gradient boosting regression, KNR, random forest, extra tree regressor, elastic net, decision tree, and MLPNM. So here, first we split into the data into the two part: X train, X test, Y train, Y test, and that is doing by using this command: train, test, split. What have to split? X normalized, Y, and test size. Test size, what will be the ratio of the test in corresponding to the whole data set? It is the 20%. So you have to write the uh, 0.2 for that. And there is a thing random number. So what is defined by using this random number? Uh, sorry, random number, random state. What is defined by the random state? When this command is splitting to the data. So how it should split the data? Like from where it have to start. So if I use a particular number from the random state, then it will split every time into the same data. Like every time if I command this, I will get the same train, same test. But if I not put any value, so it get the random state value like some random value. So for that, you will get a different splitting like every time you do this. Like you will get a different random, different train set and different test set. Maybe in the last time I show you. So now I split the data. Then you will see the data by using X train, Y train. Now I have to talk about the models. So first of all, you have to load the model. Like I just write model is equal to linear regression. And then I have to fit X train and Y train by using that model. So I fitted my model. Then I have to predict. Like I have to predict the train set and the test set by using that model. Then after the prediction, you just want to like evaluate those models. So for that purpose, you have to get the R2 value, RMSC value, and mean absolute value for the test set and the train set. After that, you want to print those values. For that purpose, print command will be used. And till this thing we have done in the last session. So now some things which are left, which were left in the last session, we will start those things. Maybe all of you have done till now. Are you able to done till now? Okay. Then maybe all of you have got these values for the R2 train and R2 test.
I am getting some error.
In which code?
I'm also getting an error.
It's showing like evaluate the model on the training data. The name white train pad is not defined.
Okay. Can you copy the error in the chat box?
Yeah,
Can you
sure.
paste that?
I'm also getting the same error.
I think I have missed something. Okay, sorry. 1 minute. Initialize, train test, valuation. Okay, please paste. Okay. Yeah, from the method that is score, so we evaluate the model train R2. Oh, sorry. I think we have missed this line. Okay, because we have not load the what is the R2 score, mean is squared error and the mean absolute error. So first of all, you have to import those things.
Okay.
Sorry, 1 minute. Here. Before the evaluation of the model. So you have, but I have used this line.
Yeah, it is there previously.
But one of you shared the code that does not have why train pred is not defined. 1 minute. Events. RT score mean squared error. Have you done this code? Make prediction. Y train pred is equal to model dot predict. Okay. I missed this code. That's why you are not getting.
Same code we got 2 times.
Okay. You have not got this code. Okay. First of all, you have to fit the model. Then you have to make the prediction for the Y train and the Y test. For the X train and Y test. Then you will get this. That's the problem. I think now the code is working, I think.
Yeah, it's now working.
Okay. Okay. So now we are doing new thing which we have not done in the last time. If you see the paper, they have used the 9 ML models. Okay. Or till now we have just used one model, linear regression. So now I'm going to use that all other models. So there are the two methods. First of all, I will do the same thing for the all the models. Okay. The other thing, there is a thing I can uh, train all the models in a single in a only in the one time, like in a one single code I write about the which like which model have to be trained and how, and they have to be evaluated. So there is two things, like I have go for the one by one for each model, and or I can write a single code for all the models. So here is a code which I have wrote for all the models. First of all, there is a linear regression, then there is a lasso, then there is a gradient boost regressor, there is a k nearest neighbor regressor, then there is a random forest, extra tree regressor, elastic net, decision tree, MLP. Now, please see here. First of all, I have import the libraries, then I initialize the model. So I have to write the model which have to be trained. So here you can see there is a like is 9 model, and then loop over model, train, evaluate, and the plot, parity plot. I will do the four things. First, I will train the model, then I will make the prediction, then I will evaluate those models, and then I will try to plot the parity plot. Oh, I think I forgot the parity plot in the last. Okay. Now, first print model name, model dot fit. It will take the a single model from here, then it will fit, then it will make the prediction for that model, then it will evaluate those model, and then it will print the uh, evaluation matrices like R2 score, RMSC, and mean absolute error. Then it will make a parity plot for train and test sets. Will make for the only test set. So I have to make it for trainer also. Here you can see every model is working one by one. First linear regression, then lasso regression, then gradient boost regressor, then KNR. Please paste this code in a single line, in a single cell. Okay. Otherwise it will not work. So here in this parity plot, you can easily find like how your data is getting predicted. Like if it is near to this line, so it is well predicted. It should be like lie on every point should be lie on this in line ideally. By seeing this parity plot and the evaluation matrices, you have to decide which model is working uh, best among these models. Maybe all of you get the output.
Yes, sir.
Okay, this is the way how you can train and evaluate your model by using a single cell. Here you created a loop which models have to be trained and you will get the output. And now if you want to like compare all the things, so you have to plot the box plot for this purpose. For the box plot, you have to add. So please see this code. Here I write about the box plot also. This is the same thing like first import libraries, then you have to initialize the models, and now you have to initialize the list. What is the list? This is the list of what things I want to store, like model name I want to store, and I want to store the train R2 value, test R2 value, train RMSC, test RMSC. Then I make the prediction and I get the values of the train MAE, train R2, train RMSC, train RMS, sorry, test RMSC, train MAE, and test MAE. Then I make a parity plot. Now these things are stored in the array. Now they have to be plotted by using these commands. Like for the R2 score, this is the like specification about the what size of the figure you want. Then we make a bar plot. Index first matrix df क्या रहेगा आपका, sorry, what will be the like matrix train R2, then bar width label, what will be the label, then what will be the color of the bar plot, then this is the same thing for the test. And now what will be the X label, what will be the Y label, what will be the title, then what will be the X tick and Y tick. X tick I want to the model name, and at the rotation of 45 degree you can tune this according to your how you want to that. So now same for RMSC, same for MA. Now if you run this code, you get the same parity plot as you get in the above code, but here one thing is added, that is your bar plot for the evaluation matrices. So you can easily compare what evaluation matrices like which model is working best. So this for the mean absolute error. This is for the RMSC, and this is for the R2 score. So here you can compare. Like if I see about the R2 score, this is for the train set and this is for the test set. R2 score should be maximum, and there will be the like a very low gap between the train and test matrices. And this for the RMSC root mean square error, and it should be low, and mean absolute error it's also should be low. So if I see the model here, you can predict which model is working best. So for now, if I see the ETR, a static regressor, have the highest R2 score for the train, but it have the highest R2 score for the test set also. So I can choose this model for further application. But in the paper, there is a MLPNN model which work best. So you can net. You cannot say like here you get this because we are working in just very crude way, as many of you don't know how to use the things. Have you got the bar plot?
Yes, sir. We got it.
Okay. Now there is a thing in the paper. They have performed the iterative testing with the random split and the data set to compute the mean standard deviation from the scoring matrices. That is called the k-fold cross validation. So, and they use hyperparameter tune by using the grid search CV. So what is the grid search CV? Like if you see your model, like any ML model have some parameters, like which parameters you can tune to get the higher, uh, you get the like you get to tune that model to get the accurate results from that model. So for the tuning the input to the parameters of that model, that is called the hyper parameters, and tuning of those parameters is called hyper parameter tuning. So first of all, I have to make a grid like first of all you have to see like at which value my model will work best. So for that purpose, you have to choose some values for the these parameters. Like I'm working for the extra degree gracer. So there is this these parameters. And if you work with the other model, so there will be the some other parameters. So you have to look for the uh, your model and its parameter. So if you want to see like which parameters your model have, then you have to see about the sklearn. Like we are working in the regression problem. So there is are these models, and there will be some other model also. So if I'm working with the decision tree. Okay. This is a parameter. Like here you can see parameters like n estimators, maximum features, n features, minimum sample split, bootstrap. So from here you can find out which parameter you have to be tuned, or you can just if you don't put any value, they will choose some by default values. So this grid is very big and it is about the 1440 uh, points. So I'm going to reduce it, just limit it to two value. For if you have a time, you can make a large grid. Still, we are working on the 80 bits. So this code will work 80 times. Please copy this code. 1 minute. Grid search. Here you can get the best model, like what hyperparameters got the best value among the all the grid. So bootstrap should be true. Maximum depth 10, minimum sample leave 1, minimum sample split 2, and estimator 100. One thing I have to add here. Please add this line in your code, because this is for the train set. As you can see in the previous one, there is only blue points, which is represent the test set. So I just want to about this for the train also. That's why I add this line. Scatter plot for the train test also. Now you can make a large grid to test like is it working correctly or not. Okay, please copy this and paste in your previous code. Please run this code. Anyone got the result?
No, still it's
Oh.
compiling.
Okay. It is actually it is going to fit 1,400 times. Okay. I have the result for this code. You will get the these parameters like bootstrap would be the false, maximum depth equal to the 20, minimum sample leaf equal to 1, minimum sample split 5, and estimator 100. So I will use these parameters and then I will run the code for this. But one thing here, there is a thing there. So we can. Okay, first we will do the same for just screen and test. Just forgot cross forward. Here the code. So I have used the best training, best parameters for the extra tree regressor, and I got that these evaluation matrices for this. So here you can see from the last plot which value you got earlier and what value for the is evaluation matrices now after the uh, tuning, hyperparameter tuning. So if I see about the R2 score, there is a 0.97 for training and 0.79 for test. So let's see. Phantom forest, caliber, boost. So So here you see this is like 0.99 for training and 0.78 for testing. But here now R2 score for training is reduced to the 0.98 and for R2 score for testing is increased 0.79. But maybe you have a question like R2 score for training is reduced because you just want to it should be like a generalization. Like if you see there is a all the training points is lie on the this line. So it is the overtraining. It is not a training like it just overfitted my model. So I have to make sure that it should not be overfitted. That's why R2 train value is get reduced by using that hyperparameter tuning. I have not shared the code. Or here you can see the data, training data is also spread around these lines. So now it is not a like a overfitting like problem. So please copy this code and paste. This is for the hyperparameter tuning. All of you got the result? Yes. Okay. So you understand what will do the like hyperparameter tuning. So you can do this for all the models also, but it will take time. Okay. So you make a grid of the parameters and uh, then train and got the output for the output from sorry for the best parameter which you got from the grid search. So there are some different other technique like random search and genetic algorithm search. So you can also use those things to get the best parameters, best hyperparameter. So now there is a thing in that work is the k-fold optimization, k-fold cross validation. K-fold cross validation is actually when we start the work, we split the data in our two parts, train and test. But there is a thing like you can't say like this train will be train and test. We choose the arbitrary, but there will be some thing in the model like there is some biasing between the train and test. Like your test give your selected test will give the best value, but it is not working in the all the data. So for that purpose, you split your data into the some part like k parts, and you use other k1 values, k1 parts for the training, and one set for the testing. And you you do this in the k times using the different portion for the testing. So that's why it is called the k-fold cross validation. And in this way, your model will be trained for all the set, and your testing will be done for all the data. So that's why. So here you can see this code. I have used these parameters and the k-fold and split 5. I'm splitting the data into the 5 parts. You can use like 10 parts. You can use 8 parts. Then shuffle true, and it means like these data set will be shuffled to each other. And random state by prediction, cross validation predict model will be used ETR and XY cross validation KF. So now you get the mean R2 score, mean RMSC value, and mean absolute error for the test set. If I reduce the size of, sorry, if I increase the size of K, you will get the different values because now the training set will be increased. Now it is like ratio is 10:90. Previously it was the 20:80. So you can use this for all the models also. In the paper they have do the k-fold cross validation for all the models. So here you can see in these plots, they have used the different evaluation matrices, R2 score, mean absolute error, and RMSC. And they got this plot like how the variance. They got the highest value for the MLPNN. And they also reduce the size further, like 4 point. Just they have use the 7 input parameters. They have used try like after using the 6, then 5, then 4, then 3, and evaluate how the parameters is correlated with the output property. So this is the output, some output of the work from the like model evaluation part. They got the very good high accuracy for the MLPNN model, 0.87 for the training set and 0.85 for the testing set. And this is the hyperparameter tuning of the MLPNN model. And this is the training set and the like parity plot for the MLPNN. And this is the sharp analysis. Sharp analysis will be done to like to see how our input properties are correlated with the output properties. That's why they have used this. Is there some thing which you can use how your input properties determine your output properties? We will discuss this in the some future sessions. So this is the predicted and the reported stacking fault energy for the different reported alloy systems. And this is the predicted value which they got from this paper, this work, and this is the reported or calculated value. And if you can see, there is a like approximately same values they got. Like there is a some uh, these are some plot they have plotted for the like ternary system, nickel, chromium, iron, nickel, chromium, cobalt, nickel, manganese, iron, cobalt, manganese, iron, uh, make a heat map for the their contour plot for the stacking fault energy. And you can take a point from this ternary compound which is taking fault energy you want. Like if you want to like 120 around 120 stacking fault energy, then you have to choose this green region and make a composition according to that. So it will lie in this region. So you take the like a percentage of the material in such a way. So it will lie in this region or in this region, in this region, in this region, in this region. If you're working same as you will do for all the plots. So these the key findings of this work. They found some features which are highly correlated, like specific heat, temperature, ionization energy, stacking fault energy, sorry, LSC variance, and L in electronegativity average. And they also find this empirical formula for the stacking fault energy. So this is how you can use the ML. So we have just finished this work now, and we will maybe. Do you have any question?
Sir, please share the slides of last session and this session.
Right. Is there any question?
Sir, how did we get the composition?
How will you get the composition? Like for the prediction, just like you have a input properties, like just input set. Okay, you have this input set. This is the input properties, and this is sorry, this is the composition, and this is your stacking fault energy for that composition. Now you don't know about the stacking fault energy for the prediction part. So first of all, you have decided these values like what will be the value of the Fe, what will be the value of Mn, what will be the value of nickel, what will be the value of cobalt and chromium, vanadium, molybdenum, silicon. So you make a composition and then take the average, sorry, then take their weight in that composition, then write here just for example, and then you will calculate these values for that composition, like these properties, input properties, and then you will use these properties as a input of that model. The similar way as we are working for the test set, and then you will get a output. Then they make a plot. Maybe you are asking about this plot, or you can just
I'm also asking that plot also how that ternary diagram came.
you can plot the ternary program like ternary composition, like you have a nickel, chromium, and Fe. So you put like the total percentage of the composition should be the 100%. So you will take like a 10 days, 20 days, and you make a some a dummy set like that have the various values of the nickel percentage, chromium percentage, and Fe. Like just I can give you an example. Just suppose I am just want to the nickel chromium Fe. Okay. So I randomly choose the ratio. Like I just choose the ratio 1, then 0, then 0. In some composition it is 0, it is 1, it is 0. Then in some composition it is 0, it is also 0, it is 1. Now it can be 0.5, it can be 0.5, it is 0, it is 0, it is 0.5, it is 0.5. Now it is 0.5, it is 0, it is 0.5. Same as you work with the different like different ratio. Like it is a 0.25, it is a 0.75, then it is 0, then it is 0.75, it is 0.25, it is 0, it is 0, it is 0.25, it is 0.75, 0, 0.75, 0.25, and 0.25, 0, 0.7. So in this way, you can make a like a composition null ratio. How you will your composition will be look like this. Like this composition will be, if I see only nickel, this will be like only chromium. This will be only Fe. But this is nickel 0.5 Fe. Sorry, chromium 0.5. Then there will be a composition like everyone is there. 0.25, 0.25, 0.5. Then for this purpose, you can take a help of the Python. Then it will give you a dummy set, and you will featureize that composition, and then you can use that as an input of your model, and then you will get the output for that. Maybe now you find your answer.
Yeah. Okay. I got this. That like we will use Python for generating that.
You can use for the Python, but for a single output, just I want to like just you give me arbitrary composition for in this ternary compound.
Okay. Let's say NI20 CR
NI20,
40, CR 40,
CR40.
and what is that? What is the next? FE.
Just for
FE
simplification, I
FE
take
40.
40.
Yeah.
Okay.
the rest.
Now if you take the weighted here, so it will be like 0.2,
And to
it is 0.4, it is
Yeah.
0.4. Okay. So now you will now you have the elemental ratio for this composition. Now you will convert into the property of that. ACR, average electronegativity, and then you can use that as a input
Yes,
for your
I
model.
know like electronegativity I can calculate, but
So,
I want to
so
know
you don't want to don't use like a for every line. So you have make a formula like just you want to choose, you want to take a average. So you have a property value like just suppose for example electronegativity values. I'm not using the actual value. Electronegativity for chromium, nickel, and Fe is just 100, for example, 200 and 300. Okay. I'm taking just for example. This is not actual value. Okay. And you want
So
to
can you explain about ECR? How is that useful in affecting the properties, and how do we calculate the ECR, elemental component ratio?
elemental component ratio formula for the elemental component ratio is given in the paper. You can see there.
Okay.
Okay. Just for electronic negativity, you have to use like you want to electronegativity of chromium. Sorry. This value. This value into electronegativity of nickel plus
Yes.
this value. So you can get for the all the set just just you have to write one time. Or for this you can also use the Python.
Okay. Sir. Okay. For,
Maybe you got
ECR,
your answer.
yeah. Sir, does ECR like affect in composition prediction? ECR.
Sorry.
We have ECR, na element component ratio.
This elemental component ratio is a like I can show you. What is this? In that paper, you can get that formula actually. This is the formula for the elemental component ratio. Xa is equal to xi to the power a, and the summation for the all the things, and then it is a like 1 over a. Okay, and you can find about this in a more rigorous way from the site reference 38.
Yeah. Okay.
If you want to read about this more. Okay. Any other question? Anyone have any other question?
Hello.
In any coding part? Huh?
Sir, again, I have one more question.
Please.
It's like I have told you one composition like 0.2, 4.4, 0.4. Okay. Let's assume that we want to predict SFE for that composition only. So
Okay.
How do we will get in that this program? I'm a bit confused. Last step.
Can you say me the composition or what you want to use?
Yeah, 0.2, 0.4, 0.4. Yeah,
0.2, 0.4,
0.4.
0.4. This is the same composition, 0.2, 0.4, 0.4.
Yeah.
So if you want to use this is 0. Right? Okay, you have to choose the value actually. That's the problem. 17. This is like about the 220. So same way you can calculate the other properties also. And then you will use as a X input for the model. Hello.
Yeah. I'm understanding all those things that I can calculate, but through ML model, we are basically predicting the SFE.
Okay. You want to how I'm doing the code for that?
Yeah, exactly.
Okay. So for that purpose, just for example, I can show you. Just load, first of all, you have to load your data. Load the data. Then you have to check the columns of your input data. You have to look like your input data is similar as the your input data which you have used in the training part. Like I have used the 7 columns, so you have to check all the 7 columns are there in your input set, which you are now giving. Then after that you have to use like I have used here the standard scaler also. Sorry, minimum axis scaler. So then you have to normalize your data. Your data if you have done previously. Okay. If you have used any standard scaler or any normalization process, so then you have to normalize. Then you will use model name dot predict and your input set. Name of input set. Okay. When you give the model dot predict, then you will get some output. So you can make it like a y pred, or you can give some other name also. And after that, you can print those values. You can combine your input and output to see the values for each composition. So that's the way you can do that.
Okay.
Okay. Maybe in the next or in the future class, I will show you how you can do that.
Okay, sir. Thank you.
Okay, because I have no like the values for these, so how can I make any
Okay.
dummy set?
Okay. Actually, I wanted to understood that how this model will work, like the final bits.
Maybe this is the way. It's just simple, but first of all, you have your like dummy data for which you want prediction. So that should be featureized also. Then you can work.
Okay. Okay, sir.
Oh, any other question? Okay, let's end this session. Thank you.
Sir, slides,
Please.
slides, sir. Slides, sir.
Slide.
Yes, sir. Both the session, last session and this session.
Sorry, I'm not able. What you are saying?
Sir, I wanted those slides.
These
Last
slides.
session, yeah, those slides. Yeah, I just
So
wanted
that
to
is uploaded
glance
in
them.
the portal actually. You can find from the like I think I have shared some Google Drive link there.
Okay,
sir,
In
fine,
the
sir.
NPTEL
If there is anything, I'll
in the NPTEL portal, there is a some Google Drive link. You can find the all the PPTs there.
Okay, it is uploaded already.
Yeah, actually, PPT and the videos are uploaded there. YouTube link of the this session or previous sessions.
Okay, I'll check. Thank
Is there any other question?
no, sir. Thank you.
Okay, thank you so much.
you. No, sir.
Okay,
Thank
bye bye. Oscar. Okay, thank you so much.